Hello everyone, so today we're going to talk about the fundamental theorem of calculus. And the fundamental theorem of calculus is actually a two-part theorem. So let's go ahead and just jump right in. So I'll state both parts of the theorem and then we'll look at both examples of how both parts apply to specific problems. So, theorem. So the fundamental theorem of calculus part 1. So let's start with the hypotheses. So we'll say if f is continuous on some closed interval a to b, then the area function that's given by an integral let me move that down here. Sorry. Then let's call it the area function a of x, which is equal to the integral from a to x of f of t dt. Again, for x in this interval, so for a less than or equal to x, less than or equal to b, is continuous as well. And differentiable on the open interval. Again, remember, you can't have it be differentiable on the closed interval because it's a limit, and to have a two-sided limit, you want to be able to have the point be an interior point of that interval. So it's differentiable on this open interval, a to b. So the area function satisfies a prime of x equals f of x. So in effect, this is kind of telling us that the derivative and antiderivative have an inverse relationship with each other. So let's think about this. So we could say that is, if we do a prime of x, that's the same as taking the derivative of the integral from a to x of this function f of t dt, and what you get is actually f of x. So if you take the derivative of the integral, you get the integrand with that being replaced by x. It'll get a little bit trickier if we replace x with a function of x, but we'll look at that as well. So that is the first part of the fundamental theorem of calculus. So let's talk about the second part. So the second part of the theorem of is probably the part that we will use more frequently. So this is the fundamental theorem of calc part 2. So the second part tells us that it shows us that the integral can be used to find a specific area beneath a curve. So if f is continuous on this closed interval a to b again, and again we say capital F is any antiderivative of little f on a to b, then the way you compute a definite integral from a to b of f of x dx is we can just do f of b minus f of a, where we're talking about capital F being the antiderivative. So the way that you can compute this is that. So it's important to think about the picture here. So the picture we're talking about, if we have some curve, let's say y equals little f of x, and we have some interval from a to b, and we want to find the area between a to b below the curve. This area right here is given by capital F of b minus capital F of a. So that's pretty amazing and very useful. We will use that quite frequently throughout the rest of the course. We'll also do examples with the first part of the fundamental theorem, but the second part just will be utilized even more frequently than that. So let's go ahead and look at some examples. Okay, so let's jump in and look at some examples of each. So for our first example, let's look at, so let's use part 1 of the fundamental theorem to simplify the following expressions. So let's say A, we want to compute the derivative of the integral from 1 to x of the sine squared of t dt. And B, let's say we want to compute the derivative of the integral from 0 to x squared of cosine of, let's say, t cubed dt. So the first example is pretty straightforward. Again, we know sine of t is going to be continuous for all real numbers, so sine squared of t is also going to be continuous for all real numbers. So the continuous hypotheses are something we don't really have to worry about. So for this one, that's all we have to do is actually go ahead and replace the variable. There's nothing tricky to do there. So the derivative and the integral essentially, quote unquote, cancel, and we just end up with sine squared of x. And that's it. However, for the second part, there's a chain rule, because if you look at the top limit of the integral, it's a quantity x squared. It's not just x. And again, for the same reasons, cosine is, we don't have to worry about continuity because cosine is continuous everywhere. T cubed is continuous everywhere. So the compositions of polynomials and trig functions are going to be continuous everywhere for sine and cosine. So if you had some other letter rather than x squared on the top, imagine that this were actually the integral from 0 to u, what would happen? So let's write something down here. Let's imagine, or let's say, suppose u were equal to x squared, then what would your integral look like? It would look like you would have the you would have this new function. You could call it g of u is equal to the integral from 0 to u of the cosine of t cubed, still cosine of t cubed dt. And what would happen is you would have a chain rule there, because you would have this other implicit function as one of the limits. So we could say by the chain rule, the derivative of this integral from 0 to x squared of the cosine of t cubed dt is some function dy of dx, which we are actually thinking about as dy du times du dx. Okay, so we have this chain rule popping out. So it's telling us essentially we have to take the derivative of this u function, and then we need to multiply that by the derivative of the integral. So what is the derivative of x squared? The derivative of x squared is just 2x. So what essentially we're left with is the derivative with respect to u of the integral with the substitution we made times that 2x quantity. Okay, and we know that since we just have u in the integral, that just would replace the value of t. So we would just get the cosine of u cubed times 2x, and we can replace u because we know that u really is just the value of x squared. So what we have here is we have 2x times the cosine, and u was x squared, so we have x squared quantity cubed. So we're left with 2x times the cosine, and remember we multiply the exponents here of x to the 6th power. So again, that seems a little bit tricky, but really you just have to apply the chain rule to any of the limits if they involve a function. Okay, so those are two pretty basic examples of the first part of the fundamental theorem of calculus. So let's look at utilizing the second. So the second part, so let's say, for this example, what do we want to do? We want to evaluate the definite integrals using the second part of the fundamental theorem. So for part A, let's say we're looking at the integral from 0 to 10 of 60x minus 6x squared dx. So for this integral, what we want to do is we want to find the antiderivative. So these are both just power rule antiderivatives. So the antiderivative of 60x will be 60x squared over 2, and the derivative of 6x squared is going to be 6x cubed over 3, and this is from 0 to 10. Again, we can pick any antiderivative, so typically what we do is just pick the one where the constant value is 0. If you chose some other constant, you would have to pick the same antiderivative, and then when you do f of b minus f of a, they would both cancel anyway. So let's just simplify this a bit. So this would be 30x squared minus 2x cubed, and then we have these points to plug in. So first you would plug in 10, then you would plug in 0. Luckily, when you plug in 0 into a polynomial without a constant term, it's just going to end up being 0. But I will write it down just in this first example anyway. So this is what it looks like when you plug in the limits and then subtract them. So what do we end up with there? We have 30 times 100, which is 3,000, and then you have 2 times 1,000, which is 2,000, and then we have minus 0 from that stuff. So our answer to the first part is just 1,000. And that is example A. Again, we are dealing with a polynomial, so we don't have to worry about any continuity issues for that example. Let's go ahead and look at another. Again, these are all going to be fairly straightforward when we're dealing with just basic antiderivative rules, but that's okay. So let's look at the integral, say from 4 to 16 of 3 square root x dx. Again, whenever you're dealing with, say, a square root or division, it's often helpful to rewrite the integral using exponent notation. So this would be 3x to the 1/2 dx. So computing this integral, we would say, all right, well, the antiderivative of x to the 1/2 would be, well, you add 1 to the power, so it would be, so the exponent 1/2 plus 1 is 3/2. So that means in front we need to multiply by the reciprocal of that fraction. So we have 3 times the reciprocal of that fraction, 2/3, and that is our antiderivative. So we see that the 3's cancel, and our antiderivative simplifies to just 2 times x to the 3/2. And what you do is you just plug in the limits and subtract. So we have 2 times 16 to the 3/2 minus 2 times 4 to the 3/2. And both of those can be computed in your calculator. So that comes out to just 112. But you can probably do them mentally as well. They're not difficult to do. You know both the square root of 16 and 4. Okay, so let's look at one involving maybe the sine of x. So let's suppose we have the integral from 0 to 2 pi of the sine of x dx. So what we want to do here is find the antiderivative. Again, the antiderivative of sine is negative cosine. So we have negative cosine of x from 0 to 2 pi, and then just plug in both limits and subtract. So we have minus cosine of 2 pi minus the negative cosine of 0, which comes out to, so let me make sure, did I forget a coefficient? Oh, no, that's the example right here, so that's fine. So this comes out to the cosine of 2 pi and 0, they are at the same, they have the same terminal angle, so this comes out to, let's say we have -1 minus minus, so then we have 2 negatives here. Sorry, all the negatives are throwing me off for some reason. Minus -1, so this is -1 plus 1, which comes out to 0. So nothing too tricky there. All right, so those are the basic examples that we will encounter when we look at the fundamental theorem of calculus part 1 and part 2 problems. Let me just highlight a couple other ones. So so if I haven't mentioned it before, let's recall some other properties of the definite integral, because these can sometimes be utilized with the first part. So let's recall some properties. Properties of the definite integral. So what I want to talk about are just the limit properties. So the first of these properties just says, say, if you have the limit, say, from a to a of any function f of x dx, this is equal to 0. If you're looking at the limit over a single value, there's not going to be any area there, right? If you're looking at some curve and you're trying to find, say, the area of a single value, you have a strip right here, but it has no width. So this has no area to it. That's all that that's saying. Another one says if you have some point in the middle, so if, let's say, a is less than C is less than B, something like this, then what you can do is you can put together and split apart integrals. So say you have the integral from a to c of f of x dx plus the integral from c to b of f of x dx. This is actually just the same as the integral from a to b. Again, we have to make sure that all of these functions are continuous and things like that, but it basically says if you have some point and you have two component areas, you can add those together. So not so tricky to see. The picture is pretty straightforward. So A, C, and B. It's basically just telling you if you take this area and add it to the area over here, you get the entire area, which is not, again, not surprising, fairly straightforward, not difficult to show. And then the third one is we have this orientation issue. So if you have the integral of, say, a to b of f of x dx, this is going to be the same as negative integral from b to a. So you can flip the limits by adding a negative. Again, we want to think about this definite integral as a signed area. So meaning above the x-axis would be correspond to a positive area, below a negative area, and the same as the horizontal orientations. Left to right would be the positive direction, right to left would be the negative direction. So just to highlight this one, so let's do a little kind of like mini example here. So e.g., let's say we have some picture. So let's say we have A, B, C. Sorry. And let's say our curve, I don't know, does this. Okay, so this is, we'll call it again, as usual, y equals f of x, something like that. Let's say this has area 5, and this has area 3. So let's just say, say we wanted to compute the integral from a to b of f of x dx. Well, that would just be 5. But if we went the other way, b, let's say we did the integral from b to a of f of x dx, well, then this would be negative 5. We just append a negative. And then similarly, if we did, say, the integral from b to c of f of x dx, well, that's the area between the second curve and the x-axis, but that's below the x-axis, so that's already a negative 3. And if you would go instead of going from left to right, you went from right to left. Let's say we started at c and then went to b of f of x dx. Well, this would end up being negative 3, which would come out to a positive 3. So we have those typical sign conventions there for these integrals. So why don't we finish there, and we can look at some more examples in future videos. So let me know if you have any problems on those in the homework. This is Dr. Lennon signing off.